Okay, we have a pool ball on an incline. There is one over there. There's a bracket that's about this shape that's keeping the ball from rolling down the incline. This sort of picture is pretty relevant, for example, to what happens if your brakes aren't working and you try to park a car on a hill. You put a block behind the wheel, right? So how does that work? It works. We know it works. How does it work? Okay, well, first thing everybody told me was that this force, which I'll write F sub grav, acts downward, okay? Just to put a label on it, that's what I want to use for the symbol. If you say gravity, that's fine. So I just ask you to do the source of the force, right? Okay? So that's good. Now, in what direction is the force of the incline? Normal force, perpendicular to the incline. We talked about it a couple of weeks ago, but now you're going to have to get that idea, okay? The incline itself exerts a force perpendicular to itself. Okay, so you have this force, which I call the normal force. Okay, what else? Well, is anything else touching this or acting at a distance on the ball? Gravity's acting at a distance, right? Mass of the earth interacts with the mass of the ball, right? And each exerts a force on the other. The ball's actually pulling the earth up a little bit. If you drop the ball, the earth comes up a little bit to meet it. But the earth has 10 times the mass of that ball. So it only moves about 1/10 as far, so you usually don't notice it, right? Well, it's not 10 times the mass of the ball, okay? It's roughly 10 to the 25th times the mass of that ball, okay? That's 1 followed by 25 zeros. So the earth, if the ball moves a meter toward the earth moves 1 over 1 followed by 25 zeros, or 0.2501, okay? 0.4 zeros, 1. Okay? Times as far as the ball does. That's not what happens. The earth close to the ball deforms just a minuscule amount. And then that ripples through the earth, and the seismometers all pick it up. Okay? Not really. It's an undetectable. Now, a good seismometer close by would pick up the impact, because then you get the impact waves. So I'm just talk about the waves that come out because of the gravitational interaction and the deformation of the earth up toward the ball. So it's kind of interesting, but you don't need to know that right now. So I'll stop talking about it. You have the normal force, you have the force of gravity. Clearly the normal force is the force exerted by the incline. And you're going to have to accept, although the demonstration I did with the meter stick and the coin last time, or the little piece of styrofoam this time, lends credence to the idea that force has to be perpendicular to the incline. Okay? So we got to know that. Okay. Now, there's a force. If this thing wasn't there, the ball would accelerate down the incline. But it's sufficient to stop the acceleration. You can analyze that by the forces, or you can analyze that actually by work and energy, but we haven't talked about that yet. It takes more energy for the ball to get up and over this thing than it gains from moving a little ways down the incline, okay? but that's later. Okay. The question is, what's the direction of the force here? Well, let's enlarge it a little bit. It's a contact force. It's just like a normal force. It's going to be perpendicular to the surface of the ball at the point, because the ball is being indented a little bit, and when that indentation, if that indentation was to restore itself to the original shape, it would push the ball back this way. Okay, perpendicular to this point. Okay? So, yeah, I'm questioning that a little bit. Okay, right now we're going to say we have a force in this direction. Okay? So it's going to be not straight back and not down. Now, at least one of you mentioned a frictional force. These three forces prevent the ball from moving. If the ball isn't trying to move, then there's no frictional force. There are better ways to explain that, but that's kind of what the three forces look like. Okay? Now, that's a finger, okay? Badly drawn finger. I'm demonstrating here. Finger's pointing directly up the incline, right? What are the forces now? Something like this, right? Okay, we're going to talk about Newton's three laws. Okay? Anybody know what Newton's first law says? Well, we got the camera on. So Newton's first law says if it's moving and there are no forces acting on it, or if there are forces acting on it but they all add up to zero as vectors, so that the net force is zero, the total of all the forces is zero. If the thing's moving, it's going to keep moving, and it's not going to change its direction because it takes a force to change direction. And it's not going to speed up or slow down because it takes a force to speed things up or slow things down. Okay? Does that make sense? That's not our usual experience, because things that are moving seem to just kind of naturally come to a stop, right? If you eliminate all friction and all other forces, or balance all the forces, like for example, you're driving down the road with good cruise control, you're maintaining more or less a constant speed, right? If you're not going around a curve, if you're on a straight road and driving straight on that road, if you're on a straight road, you really do want to drive straight. Then there's zero net force. Okay? You have gravity acting down, you have the road pushing back up, maybe at an angle. You have the tires pushing back on the pavement so that the pavement pushes the car forward, okay? You think of the tires pushing the car forward, but the tires have to push back on the pavement in order to push the car forward. If the tires are on slick ice, they don't push the car forward very well, do they? That's because the ice doesn't push the car forward. The friction between the tires and the ice is maybe insufficient to overcome a little bit of a grade, a little bit of an incline, okay? So maybe you sit there spinning, you don't go forward, you don't go backwards, in which case your net force would be zero. If you're not moving, your net force is zero. If you're not changing velocity, your net force is zero, okay? So again, the three laws are kind of intertwined, but the first law says, and the usual statement is an object in motion remains in motion along a straight line with no change in its velocity unless acted upon by some net force. They gives a statement, and the statement varies a little bit from one author to another, but that's the essence of it. That's Newton's first law. I see you guys are writing that down, that's good. Okay? I'll give you a minute to go ahead and write it. You don't get too loquacious there, we'll keep the tape running so we have a continuous idea here. Okay? Newton's third law says that often for every action there's an equal and opposite reaction. In other words, forces occur in pairs. If I exert a force on you, then whether you do it actively or passively, you exert a force back on me. If we're both standing on skateboards and I push you and you're not doing anything, you still push me backwards, right? That's a passive push. I'm doing an active push, but you would passively push me back because the force I exert on you has to be met by an equal and opposite force. Okay? We talked a minute ago about how the force of gravity pulls the ball down and pulls the earth up. Okay? If I drop the ball, I mean right now, the ball is sitting on the table, okay? Well, that's a little more complicated, but that's an important idea. Okay, gravity is pulling the ball down, the ball is pulling the earth up. Okay? Now, the earth doesn't go anywhere, neither does the ball. Why is that? It's sitting on the table. Okay? The ball exerts a force on the table. The table exerts a force on the ball. Okay? Because of the ball, the table exerts more force on the floor, and let's just say the floor is part of the earth, is pretty well anchored into the earth. It counters the tendency of the ball to pull the earth up. Okay? There's a whole chain of forces there. But you have Newton's third law, forces, force pairs. Okay. Gravity pulls the ball down, pulls the earth up. Okay. So you're going to see a lot of conceptual problems in the assignment that will be due on Monday. that help you sort out force pairs and think about forces in a more sophisticated way. So I wanted to talk about that a little bit, but I'm kind of going to lead you to the textbook because I think they do a really good job of that. But I wanted to illustrate it here and also get into the idea of drawing these pictures. Now the other thing about these pictures, if I draw these three forces, head to tail, if I've drawn them accurately, which I probably haven't, I think I drew the normal force a little bit too short, but let's see. Okay. Here's a normal force. Okay, so let's just draw the normal force here. Is that the same length? The same? Pretty much the same. Gravitational force is down here. And this force is here. Well, they don't add up to 0. They add up to this force here. Resultant force is not the 0 force. This means that I didn't draw the picture right. My picture wasn't completely accurate. Okay? So, resultant force isn't equal to 0. But the resultant force is 0 because that ball wasn't going anywhere, right? Ball was sitting there, not accelerating. Okay? Meaning, since the ball was not accelerating, then that force on it had to be 0. So either there's some other force other than these three, or I didn't draw it accurately. I could modify it. I could say, well, okay, if I know the gravitational force here, and I know the normal force, then this has to be that third force. Okay? They have to be like this. We say these things are in equilibrium. So the sum of the forces is 0, and this is what your picture looks like if the sum of your forces is 0. And that's the main point I want to make. If you were to draw this accurately, the sum of your forces would have to be 0. There's another picture I can draw. I'm going to put my x-axis along the incline. My y-axis is going to be perpendicular to the incline. Now, I don't think I have a good perpendicular. My normal force, it didn't really draw perpendicular. That angle's supposed to be 90 degrees, which was about 83 degrees or something. Okay? I didn't draw the normal force. Did a good perpendicular. But the point is that if I draw it right, the normal force right, it's going to go along the y-axis, and the incline is in the direction of the x-axis. If you're analyzing forces on an object on an incline, that's the way you want your your coordinate system to be oriented. In that case, Okay, I'm gonna get fancy with colors here. I'm going to use blue chalk for the normal force. The normal force has 0x component, right? The normal force is just purely in the y direction. Every other force has an x and a y component. So that the gravitational force is equivalent to a force acting down the incline and another force acting in the negative y direction. The y direction is not up and down anymore because the x-axis has to be parallel to the incline. Now, you don't absolutely have to have the x-axis parallel to the incline, but it's really easy to analyze the forces if it is, and it's hard if it isn't. Okay? So, here's your gravitational force. Then we're going to call this F grav x component. And F grav y component. Okay? Now, we're going to get rid of F grav. Because as I said, F grav is equivalent to these two. So I'm going to leave these two and get rid of F grav. So gravitational force now is seen as the resultant of a force parallel to the incline and a force perpendicular to the incline. Okay? Now, the force of the block, let's call it, I didn't label this, let's call this that metal bracket I used. Doesn't look much like a block, but it functions as a block. I'm going to call it a block. Think about putting a block behind the wheels of your car. Okay? I'm going to make that vector. The components of this vector I'm going to make draw as green. So we have x component of F block and the y component of F block. Well, the picture is kind of tangled up with things, so I'm going to redraw these forces. There's your normal force. The gravitational force is represented by these two vectors and the force exerted by the block by these two vectors. In the y direction, it looks like I missed my right angle there in the opposite direction, but I'm trying to compensate. Got a bad angle looking at the board and I'm not being that careful. So. But I'm going to draw it as a picture. this vector in the y direction, plus this vector in the y direction, plus this vector in the y direction, give us a zero vector. In other words, if I put this head to tail with this one's going to be equal and opposite to. The sum of these two here is equal and opposite to this one, okay? That's represented by the fact that the sum of the forces has to be zero, okay? Okay. Good to see you.
Good to see you as well.
Okay. Similarly, these y forces have to be equal to zero, okay? And they have to add up to zero. Now they don't, the way I drew it, this force is much bigger than this one, right? Okay. This force and this force. Equals zero. That is not so as the forces are drawn, but that is the condition. What we say is the sum of the y forces is zero. Now your text might write these not as vectors, just as vector components. I choose to write them as vectors because that's why I wrote them up here. Because they pretty much are vectors. Don't disagree with your book, but I have a preference for writing them as vectors. Okay. Does that picture halfway make sense? Yes, no, yeah? Tell me. Yes, no? Okay. Yeah, well, some of you are trying to agree with me. Okay, well, hopefully it does. Just let that be kind of a little introduction, okay? Most of what you look at the beginning of chapter 4 involves Newton's first and third law, okay? So we have, and talking about action-reaction pairs, there aren't a lot of action-reaction pairs in this one, because the reaction to the gravitational force is a force exerted by the ball in the earth, okay, and stuff like that. But you'll sort that out by following the textbook's introduction, which is better than what I could explain. Then we'll follow up on it and clarify any problems you have with it. Newton's second law, I'll just mention. Well, if I take this block away, these forces no longer add to zero, right? Okay. Well, these forces and this force do add to zero because the ball isn't going up or down, right? And that's still going to be true. It's not going to go up off the incline. It's not going to go down through the incline, assuming your incline is strong enough. Okay? So there's no acceleration in the y direction. An acceleration is a change in velocity. It involves a change in velocity, okay, which involves a net force. If the net force in the y direction is zero, well, if the acceleration in the y direction is zero, as it is, if that ball's rolling down the incline, that's why these forces add up to zero, okay? If you introduce another force, put a magnet out here and a steel ball, it could come up off the incline, right? In that case, the forces wouldn't necessarily add to zero. The forces in the y direction wouldn't necessarily add to zero. Forces in the y direction add to zero because the incline is strong enough to support the ball and there's no external force try to pull the ball up succeeding in pulling the ball up off the incline. Okay, so you're just stuck with the X forces. If you remove this force, what have you got? You just got the component of the gravitational force down the incline. Now, you probably do have a little bit of friction up the incline, but rolling friction is very small, which is why that ball moves smoothly, with just a little bit of incline, right? Okay, so yeah, that all needs to be sorted out. So I'm just kind of talking about some of the things we've got to look at. And we'll investigate some of this in lab Friday.